Discovery at Home. My name is Adam, and I'm a science educator at the Discovery Center. We're sorry for the delay this morning. We had some minor technical difficulties, but we are back in business. So now, today, you're in for a shocking experience because we will be talking about static electricity. Not only will we make our own scientific instrument, but we will go on to use it to test the ability of different materials to build up static charge. Did you know that the word electric originates from ancient Greece? The ancient Greeks observed that when a piece of fossilized tree sap called amber was rubbed with animal fur, the amber would attract small particles like dust. We can see the same effect today. Over 2 millennia later, in the much more recent past, the Greek word for amber was used to describe a newly discovered particle that carries electric charge. Have a look at this word and see if it I'm going to try to pronounce it for you. It's pretty much Greek to me, but I listened to a translation, and to my Anglophone ear, it sounds like electro. The word was the origin of the electron, a tiny negatively charged particle discovered in 1897 by J.J. Thomson. While we're still waiting for others to join the stream, I have some interesting facts about electricity for you. For starters, our own bodies use electricity to do very important things. Our brain cells, our neurons, use a combination of electricity and chemicals to communicate with each other. So anytime you have a thought or do an action, your brain is using electricity to make this happen. Did you know electricity is also responsible for our heartbeat? If you've ever seen a diagram like this in ECG, or saw it in a hospital monitor in real life or on TV, this is a measure of the electricity controlling the heart, taken from a machine called an electrocardiogram. In grad school, we had a medical instrumentation lab where we had to build our own EMG, which is an electromyogram. We had skin electrodes on our arms here, and if you notice here, your muscles for flexing your fingers for your grip are all in your forearm. And you can probably see my tendons moving here in my wrist, and you might see some flex in the forearm. So the electrodes on the arm were able to detect the electrical signals from our nerves. And we had a kind of a pressure sensor in our hand, so we could correlate our grip strength with the electrical signals. Because the way your muscles produce more force is by engaging a higher percentage of muscle fibers. So as you increase the strength, the percent of engaged muscle fibers would increase, and to make that happen, the electrical signal would have to increase. And we wrote some code to collect and process and display that, and we were able to process that and look at it and correlate it with the grip strength. It was pretty cool being able to do that almost from scratch ourselves. A second and a different type of electricity fun fact for you is that some animals use electricity or detect electricity to help them hunt. A platypus can sense the electrical impulses from their prey using their very sensitive bill. A platypus bill is covered with almost 40,000 electricity sensors called electroreceptors. Another animal that uses electricity is the famous electric eel. But instead of detecting electricity, they use it to shock their prey and to defend themselves. My last electricity fun fact is that static electricity can help some animals and insects climb smooth surfaces. Geckos, is that the right way up? I guess it doesn't matter for this guy, because geckos are particularly amazing at using electrostatic forces to climb. The gecko's toe pads are designed with many tiny hair-like structures, greatly increasing the surface area. The difference in charge between the surface of a gecko's feet and the surface it's climbing helps it to grip or stick. This is why geckos are the masters of hanging upside down, even from a single toe sometimes. Spiders take advantage of the same effect to scurry up walls or stand upside down on the ceiling. Humans even take inspiration from gecko feet to accomplish some amazing climbing experiences. Elliot Hawks and his colleagues at Stanford University have developed a gecko-inspired invention to help people scale up a glass wall. Their invention could lead to boots that help astronauts complete future spacewalks, all because of electrostatics. Now that we've given everybody time to join, let's get started thinking deeper about electricity, and static specifically. For those of you who've joined after the beginning of the stream, welcome. I'll introduce myself again and fill you in on today's topic. My name is Adam, and I'm a science educator at the Discovery Center. Today's workshop, called Ecstatic for Static, is all about static electricity. We'll be testing the ability of different materials to build up a static charge, and we'll use our own handmade scientific instrument called an electroscope. Let's get started. Static electricity is one of two categories of electricity. The other type is current electricity, a current like a flow, like a current of water. We'll talk mostly about static electricity today, with a little sprinkle of current here and there to help us understand the similarities and differences between the two. Let's start by brainstorming about static. What do you already know about static electricity? Can you think of times that you've experienced static? Do you notice, if so, do you notice a pattern with the seasons or the location where you experience static? Why do you think that might be? I myself notice lots of static when drying my clothes, and these shirts are kind of bad for it. And not when they're hanging outside in the clothesline to dry, but I definitely notice it when they're in the dryer, especially if I've forgotten to do one small step of adding a dryer sheet. Have you ever noticed your clothes are sometimes clinging after they come out of the dryer or make crackling sounds when you pull them apart? Have you ever put on a favorite t-shirt and noticed a sock stuck to it? What do you think is happening when the clothes are tumbling around in the dryer that makes this happen? Stay tuned for the science behind static, and hopefully you'll be able to explain this sticky business that happens in the dryer. And remember to share your science with us. We'll be checking Flipgrid, Facebook, and Twitter for your submissions during the break. Don't forget to tag the Discovery Center. By submitting your science, you'll also be entered into our Show Us Your Science contest for a chance to win a Science at Home prize pack. So now that we've brainstormed a little bit about our own experiences with static, let's dive deeper into the science of static and today's activity with Jill.
Hello and welcome to the Ecstatic for Static workshop. My name is Jillian and I'm a science educator at the Discovery Center. Do you know what ecstatic means? It means joyful excitement or overwhelming happiness. I don't know about you, but I get so ecstatic about electricity that sometimes my hair stands on end. I'm just joking. That's actually the static electricity that can make my hair stand up, and in a little bit we'll learn why that happens, see it in action, and learn why this workshop actually does make me very happy, because I get to play with a cool piece of scientific equipment, the Graaff Generator. Just like we name certain subjects within science, for example, chemistry for the study of chemical elements, or biology for the study of living organisms, we also have a name for today's science topic, and that is electrostatics. Electrostatics is the study of stationary electric charges or electrical fields. There are several different devices we can use in the study of electrostatics, two of which we will talk about today: the electroscope and the Graaff Generator, my personal favorite. During today's workshop, you will learn about electrostatics, specifically static electricity, and we'll test the ability of different materials to generate static charge using an electroscope. Before we start our test, there are a few things we need to know, like what exactly is static electricity and where does it come from? To get us started, let's talk about charges. Charges come from atoms, the smallest building blocks of all matter around us: solids, liquids, and gases. Atoms have positively charged protons, negatively charged electrons, and neutral charges called neutrons. These have no charge. Electrons are the smallest of these particles, and they spin around the outer part of the atom, which makes them the easiest to transfer between atoms. When charges are brought together, this is where the fun happens. Two different interactions can occur depending on which charges are brought together. The interaction between the charges is either attraction or repulsion. I've got some model charges here to talk about. So we'll imagine that our reds are our positive and our blacks are the negative charges. Now, attraction is an invisible charge or an invisible force that pulls opposite charges together. For example, a positive and a negative charge will be pulled together or attract. Now, repulsion is just the opposite. It's an invisible force that pushes the same charges away from each other. For example, if I have two of my positive charges they will push away or repel. The same will happen for two negative charges brought close together. They will push away or repel as well. We will see these two interactions shortly using some different materials. Now that we know more about charges in general, it's time to talk about static and gather some information that will help you as you carry out today's activity. Static electricity is the buildup of electrical charges on the surface of a living or non-living object, including our own bodies. The word static on its own can be defined as lacking movement, action, or charge. So static electricity gets its name from the fact that charges are not constantly moving in the same direction like we see with current electricity flowing through wires. This, however, does not mean that the charges do not move at all. When we're talking about static, the charges can and do move. They just don't flow constantly. We often see charges jump as a spark, and I can think of a very visible example of static in which charges move a very long distance. Can you guess which example I'm thinking about? I'll give you a hint. Even though most static charges are harmless to our health, this example could be very dangerous. If you guessed lightning, great job. Lightning is the largest example of static charge, both in distance traveled and the magnitude of the charge. Even scientific equipment designed to create large sparks cannot compete with lightning. Some large Van de Graaff generators, which are several stories high, create sparks that can span across the laboratory. But lightning tops this at an average distance of 9.66 kilometers traveled. To help you better visualize that difference, that's more than 9,000 times the height from the floor to a doorknob, or just under 6 times the distance from the Discovery Center to Citadel Hill. Lightning also carries a huge electric current of about 30,000 amperes, and that's very big. When we talk about safety with electricity, the thing we're most concerned about is current. Current is a measure of the number of my little electrons flowing. And while a large number of charges can build up on a surface, creating high voltage, most day-to-day occurrences of static are safe for humans. That's because very few of these charges are actually transferred, meaning the current is low. Thankfully, the static generator I have here today can create some shocking results with low current, so it's safe for me to get a zap from. So I talked a bit about static charges moving, but how are they actually transferred? Well, they remain on the surface until that surface touches something else. Charges are transferred when the materials simply touch each other, or when they are rubbed or pressed together, or even when materials are pulled apart. Some materials prefer to donate or give away their electrons to other materials and become positive, like my pie plate here, while other materials are better at attracting electrons and becoming negative in charge. The amount of charge transferred depends on a material's ability to donate or accept charges, and not all materials build up static as well as others. But that amount of charge transferred can be increased with some increased friction. If we rub materials together, we can transfer more charges. A classic example of transferring charges takes me back to my childhood, and you can even try it at home. As a kid, I noticed when I hid under my blankets at night, sometimes I could see sparks, especially if I was wearing soft flannel pajamas. I could even make lots of sparks fly if I rubbed my feet or my legs against the blankets. Have you ever noticed this? The sparks I saw were charges jumping from one material to another, either from my bed sheets to my pajamas or from my pajamas to the bed sheets. I increased how many charges were transferred by increasing the friction through rubbing those materials together. Can you think of any other examples of static in action? Have you ever received a zap from static charges? Why do you think some of these zaps are more or less painful than others? I touched a little on electrical safety earlier, but I really want to stress the difference between the static electricity we'll experiment with today and the current electricity running through wires to power our lights and appliances. Day-to-day experiences with static might create a slightly uncomfortable zap, but are pretty safe because only a few charges are transferred to our bodies. With the current electricity traveling in the wires in our home, there are many more charges flowing, or higher current. And higher current traveling throughout our bodies can be very harmful. This is why at some point in our lives, most of us are told never to stick a metal object like a fork or knife into the toaster, and never stick anything besides an electrical plug into a power outlet. Although generally safe for us, static can be problematic for electronic devices because they have very sensitive circuits. Bigger static charges from my Van de Graaff generator, for example, should be kept away from things like cell phones or computers and medical devices that rely on circuitry like pacemakers or insulin pumps. Now that we have a grasp on static, let's dive into some demos to help us better understand these concepts and have some fun with electrostatic forces like attraction and repulsion. My first demo for you is the classic balloon and hair demo. This will help us visualize the difference in transferring charges between objects when they're just touching versus adding friction. When I just touch the balloon against my hair, not much really happens. Maybe a few charges are transferred, but the effect is not large enough to be noticeable. When I increase the friction between my hair and the rubber of the balloon, however, we will get a noticeable effect. As I rub the balloon against my hair, electrons are transferred from the hair to the balloon, leaving an overall net positive charge on my hair and net negative charge on the balloon. Check out what happens when I pull the balloon away from my hair. Ooh, I can feel it. My positively charged hairs are attracted to the negatively charged balloon. When the balloon is taken away completely, and I'm going to give it a little more friction first, some of my hairs should still stand on end because all of those positive charges in my hair will repel each other or push away. Let's see. So I still have a few being pushed away, and they are in my face. Now it's time to bring out my favorite part of today's workshop. This piece of equipment is designed to create a buildup of charges on its surface, aka a static charge. Our Van de Graaff happens to build up a net positive charge on its sphere. It does this with the help of a rubber belt on rollers driven by a motor. Negative charges are collected on a metal comb inside of the sphere and are carried away by the belt. I won't get too much more into the nitty-gritty of how it works because it gets a little complicated, and of course, we want to see it in action. There are two other things I need besides my Van de Graaff to show you this demo: a grounding wand and a stool with some rubber feet. All right, now that we're set, the grounding rod is very important because it provides me with a constant connection to the ground or the earth, and therefore gives me a constant supply of electrons. This is because it's connected to the machine through a cord, and from the machine through another cord, all the way to a plug, which has that third prong right on the bottom, ultimately connecting it to the ground. Having this connection allows me to balance out the charges from time to time, and doing so makes sure we don't build up too big of a charge, allowing us to see a spark. Now let's just pause there for a minute. Before I can show you a spark, remember I said electronics and static electricity don't mix well. Well, in our studio we have a lot of computer equipment behind the scenes that I don't want to mess with. So I'm going to throw to a clip of me earlier where I had some sparks flying in another location. Any guesses why those sparks were happening? The spark that we see is actually electrons being pulled from the wand. Remember that electrons are negatively charged and the ball here is building up a big positive charge. So what we are seeing is opposite charges being attracted. The smaller negative electrons are being attracted to the much larger charge on the sphere's surface. The other important part of my demo is that stool. I mentioned that it has rubber feet, and this is because rubber is a good insulator from electrical charges. An insulator is a material that electrons do not easily move through, so very little electrical current can flow through it. I use this to show off a gravity-defying, hair-raising experiment that's even more dramatic than the balloon. Before I show you what happens with me, let's see what happens with my friend Harry George. Again, we'll have to do this outside of the studio to make sure our computers stay safe. Right away, we see their hairs raising up. The hairs have become positively charged, and all of those like or same charges are now repelling. What do you think will happen if I bring the grounding wand to the sphere while my friend is on top? Well, the wand provides a constant source of negative charges, so this means not only will George's hair be attracted to the negative charge and fall back down, but George will also get a little zap from those jumping electrons. It's time to get set up for today's activity. We'll start by creating the apparatus we need, an electroscope. An electroscope is a device that detects the presence of an electrostatic charge. Here's a picture of an electroscope that's still used to teach physics today. So my electroscope has a testing surface at the top to bring an object near, connected to a copper wire that suspends two foil leaflets inside a glass container. You can tell when a charge is present by the movement of the foil leaflets, and we can get a rough idea of the amount of charge by observing how much the leaflets move. We will make a simplified version of the electroscope using common objects. To create your electroscope, gather the following materials. You'll need aluminum foil, an aluminum pop or juice can with the pull tab still attached, a paper or styrofoam cup, scissors, and electrical tape. Masking tape will also do if you don't have any electrical tape handy. Let's start crafting. First, invert your paper or styrofoam cup and tape the aluminum can to the cup using electrical or masking tape. You'll want to position this so that the tab is vertical, just like this. Now, cut two thin strips of aluminum foil. Approximately 4 centimeters long by a half a centimeter is a good size. You could make them a little smaller or larger if you'd like. When your strips are cut, you'll want to squish one end of each strip to make a little thin hook. You'll then hang these loosely from the can tab so that they can hang and suspend freely. There we are. Your electroscope is now ready to try out. Now that we have our apparatus, it's time to dive into the deeper science. The first step for you is formulating your testable question. Scientists often call this testable question the purpose. What sort of questions might you want to ask about static electricity? I already have a question in mind. My question is, which of my available materials can build up the most static electricity or charge? Let's work with this testable question today to continue designing our activity. With your testable question in mind, hypothesize a reasonable result. This means making an educated guess about the relationships between variables in your experiment. Looking at the materials I have available on my table, I hypothesize that Harry George here will build up the most static charge. And, well, George decided to take a nap. But what are variables, you might ask? A variable is any factor that can be changed, measured, or controlled during a scientific experiment. It's very important that you identify possible variables and intentionally control those variables during each trial. We need to control as many variables as possible to determine a cause and effect relationship. For example, that the properties of one material caused it to build up the most static charge. Think about which parts of your experiment you should keep the same for each trial and which parts you will change each time. Write these variables in the table found on the learning guide. I'm going to add Harry George to my materials to trial, and I'm going to keep my washcloth the same for each trial, as well as the amount of friction that I use to build up charge. So I've chosen to keep a few things the same and to vary others. I will rub my same cloth against a different material each time to build up charge, and I'll make sure that I'm rubbing that material the same amount of times so that I'm using the same amount of friction. Now that I've helped you through those important considerations, it's time to design and conduct your experiment. Choose the materials you'd like to try with the electroscope, like my furry animal here, and decide how you will build up charge in these materials. It might help you to write your thoughts down to guide you through each trial so that you are following the same guidelines for each trial. This will make it easier for you to analyze your results later. Once you've designed your experiment, it's time to collect, record, and analyze evidence. Build up charge in your items using the method you decided during the design of your experiment. Decide how you will collect evidence using the electroscope. I'm going to try and charge up my acrylic wand here using my cloth, and I chose to bring it close to my electroscope to gather my results. Wonderful, so I saw an effect there. Now it's important to record your findings in the table and be as specific as possible so it's easy to draw conclusions. I might want to say my foil leaflets moved maybe 2 centimeters. All right. Look over your findings or evidence and see if you notice any patterns. What are the similarities and differences between each trial? Once you have analyzed your evidence, draw conclusions based on this evidence. Based on your results, which materials built up the most charge? What evidence do you have for this? Of my materials, the item that built up the most charge was the styrofoam bowl. I could tell this because it caused the most and the quickest movement in my foil leaflets. Awesome! As a scientist, it's important not only to seek knowledge through scientific inquiry, but to use this knowledge to inform others in our communities and around the world. So the last step I will leave you with today is to encourage you to communicate your findings. Tell a friend or family member about your findings or share them with us on social media. What did you learn about static electricity that you can share with others? And how could this knowledge help them in their daily lives? It's almost time for me to say goodbye, but before I go, it's important to note that we still have a few steps to consider before completing our test. I'll leave this to Adam to discuss with you after you've communicated your findings. Thanks so much for joining us today to learn all about static electricity. I hope you had a positively shocking experience. Now, let's zap back on over to Adam.
I hope that background information was useful to you and that you're well on your way to start your activity. Viewers, with Jill's help, were you able to answer my question about static in the dryer? Why do the clothes cling to you or to each other? If you got distracted by Harry George and didn't think about it, that's okay, I understand. I'll fill you in. When the dryer spins, it causes the clothes to tumble around and rub against each other, and that creates a lot of friction, transferring electrons. The clothes feel clingy because of the force of the attraction between positive and negative charges. You may also hear crackling when you pull the clothes apart. This is the electrons jumping back towards the protons that they're attracted to. Just like sparks jump from Jill's grounding wand to the Graaff Generator, but not as powerful. You might have noticed that I said I feel the static cling the most when I forgot to add a dryer sheet. This is because dryer sheets were invented to help neutralize negative charges building up on the clothes in the dryer. These sheets are coated in a fabric softener chemical that has lots of positive charges. The heat from the dryer melts the fabric softener so it can coat the clothing, bringing with it many positive charges. These positive charges help balance out the negative charges that have accumulated on our clothes. Thanks to science, when you get softer, more comfortable clothing that won't zap or cling. Now that you're all set with the science behind static, some examples, and most of the steps for your test, it's time for you to go build up some charge. If you're tuning in later and missed my intro or the background science with Jill, now is a good time to rewind and watch the content you missed because it will help you to complete today's activity. If you can find you can also find the learning guide with suggested supplies on the Discovery at Home webpage. As you carry out these trials in your experiment, make sure to show us your science. We'd love to see what you came up with. If you'd like your activity to be included in the live stream, you have until 5 minutes to 11 to send it in via Flipgrid, Facebook, and Twitter, so I can get it into the presentation. Make sure to tag the Discovery Center in your social media posts. When you send in your science, this also enters you into our Show Us Your Science contest for a chance to win a Science at Home prize pack. So tune back in at 11 so we can so we can finish the last few steps of our test and show off your science. I can't wait to see your results. Hello and welcome back. I hope you had an electrifying experience during the break. Now that you have a better understanding of static, it's time to finish our test by predicting the results of a similar experiment, and we'll have to justify that prediction. We'll also evaluate limitations and improvements. Let's pause for a moment to consider this. If you did this experiment again with different materials, can you predict what will happen? What evidence and reasoning do you have for this prediction? I'm going to try some materials here, and I think I'm going to have a limitation to talk about. Let's start off with one of these. I haven't had much luck with this one yet, so let's try it live. My prediction would be acrylic should work. I should be able to transfer some electrons onto the insulating plastic, and I have a bit of experience with this one. I had problems with it, but let's save that for limitations. A little better there. Do you see? Oh, good, a little bit. Let's try on the other electroscope. It's always nice to have double, especially on these homemade ones. A bit more movement there. Certainly not a lot of action on the acrylic. Let's try a different plastic. How about now? Still not much there. I have a limitation to talk about for you. Since I'm on live TV, I'm a little nervous even if I don't look it, so I might have sweatier hands than usual, and the humidity might be a problem getting in the way. That's actually one of the tricks for if you have really sticky clothes come out of the dryer, if you forgot to put the dryer sheet in. Some people will spritz it with a little bit of water to cut down the static. Unfortunately, that trick isn't being useful for me. That might be a limitation to my live testing. So I'm going to take the hands out of the equation a little bit and choose a material like this. So this is a classic one, right? We've definitely seen static build up on balloons. Nice latex surface, and I can keep my hand well away from my static area. And it's non-conductive, so my potentially too sweaty palm here shouldn't affect my static side that I'm going to keep my hand off of. Let's go. Okay. Oh yeah, no problem there. Let's do another one for you. Much better response there. So if we think about isolating variables, there's a few changes there. There's the change in material, and there's also the potential impact of the hand. So we haven't isolated those two variables. If I had some more time, I could do something like maybe put on gloves so they're dry on the outside, and that could help isolate the variables of having hands that are too wet. But let's continue. Let's keep going on. So now that I've tried some of these different materials with the electroscope, I'll have a look at some of your submissions and see if I can make a prediction, and then we'll watch it through to see the result. I encourage you to have a look at what others submit on Flipgrid and see if you can predict their outcome based on your results. And I've been seeing submissions continue to come in, so there's probably more Flipgrid submissions that you'll be able to work with that I didn't get the chance to queue up for my presentation. If you haven't shared yet, like I'm saying here, you can still submit your work to us to be included in the Show Us Your Science contest too. Don't forget to tag the Discovery Center for your chance to win a Science at Home prize pack. Let's have a look at some of these materials now. So our first viewer here has an electroscope setup, and I made sure to watch this so I see some of the materials they're going to use. They have some, looks like they found some pencils and pens. So those are materials that we think should be pretty insulating: woods, plastic, paint. So I would expect them to be able to generate a good static charge. But as I've already talked about, there's some limitations that we might not realize right off the bat. So let's have a look, and then we can talk about it. I don't see any reaction from that pencil. I just noticed something that I missed on my first read through, or my first watch through, and I'm glad I noticed it, because I think this isn't so much a material problem as it is an instrument problem. And this caption here, the electroscope not working, might be what reminded me. If you look at the design on the electroscope, the tab for the pop can is horizontal. And if you look at the ones that Jill was talking about, so it made a point of putting them on their side so they can hang loosely. So I am very suspicious that the problem here is that the leaves can't swing freely. And that's something that I was messing with and trying to get them really well tweaked. That's what happens when you're making something handmade. So there might not be a thing wrong with this besides that little bit of position. So my strong suggestion to you is rotate that can 90 degrees and make sure those leaves are hanging nice and loosely so they can move freely. Let's have a look at our next viewer. Here goes. Got plastic blue, expecting a big reaction. Lovely. Those look like very freely moving leaflets. I'm going to play that again so we can watch it. Thank you very much. I'm really happy with this kind of format because you get to see what other viewers have made, making the same sort of instrument. So see how free that movement was in the leaflets? If you want your instrument to be sensitive and deal with like lower strengths of charges, then make sure they swing really freely like that. Our next viewer is our friend Nicholas. I had trouble with his file though, but I didn't want to just not address it. So you should be able to watch it on Flipgrid. I was able to, but I couldn't get the file on the fly for some reason. So I encourage you to check out Nicholas's and any other submissions on Flipgrid. So that is it for my submissions for now. So I have a couple of questions that came in. One was asking about I've heard about attraction and repulsion for magnets. Is this the same thing? The answer is yes and no. Because electrostatics and magnetism all kind of come from the same unified electromagnetism. But then there's also some differences. We're talking about charged particles when we're talking about electrostatics, but then there's also the magnetic poles of north and south for magnetism. So this becomes a bit of a bigger question, and they sometimes overlap. I'm thinking of a scientific instrument, like a GCMS, that has the mass spectrometer on the detector, and they have a stream of charged particles going through that they're detecting, and then they can use magnetic fields that they can control to control the path of those charged particles. And so they harness that interaction between magnetism and charged particles in that detector that you can actually use in university. What else do I have? I have somebody who was trying to build their electroscope and didn't have a styrofoam cup handy. Well, the styrofoam cup isn't so much special in itself. Its job is to be an insulator to insulate your instrument from the table. Styrofoam is a good choice for it, and we had some sitting around in the office. But if you choose anything that's an insulator to isolate your instrument, you should be fine. Off the top of my head, dry glass and ceramic, so like glasses and mugs, those might be things that work well for you. So our last step for today's test is evaluating limitations and improvements. And even though that's the last step, you saw me kind of talk about it as I was going a bit. I try to do that after I did my tests. It's important to think about what things may have affected your results or made it harder to draw accurate scientific conclusions. Besides the material chosen for each trial, can you think of anything else that can affect static electricity and may have impacted your results? That wasn't jazz hands, that was kind of a hint. Was your apparatus, your electroscope, working as intended, like we were talking about the leaflets? Were there any variables you forgot to control or were not able to? How might they have affected your experiment? During my trials, I noticed that the foils of my electroscope were not moving very much. On closer examination, I noticed that the hooks on the strips were squeezed tightly against the pop tab. So my leaflets would move a little bit, but not enough. It was making it hard for them to move freely. So this likely affected my early results because even larger static charges probably couldn't move my foils very well. I made a modification or an improvement to my design, allowing the foils to hang more freely and more loosely. Oops, gotta watch the hand talking with the busy table. So after I made the modification, allowing the foils to hang more freely and more loosely, I redid my trials. I did notice a difference in the movement of the foils while collecting my data the second time around, which allowed me to draw a conclusion about the material's ability to build up static charge. While thinking about limitations, I realized that I also didn't control a variable that could affect my results, the size of the materials I was testing. Some materials I tested were larger than others, which means more surface area to build up or lose negative charges. If I were to do this experiment over again, I think I would control the variable of material size and choose materials that I could cut or shape to be the same size. There's even variables that we almost unintentionally control. I conducted all of my trials here in the lovely Climate Control Discovery Center. With today's weather forecast, I'm sure it's a lot warmer and more humid at my place. How do you think humidity might affect static electricity? I ended up unintentionally talking about that a bit. If in your own experiments, what limitations did you notice and what improvements could you make if you were to redo your experiment? I encourage you to send us a follow-up video or message using Flipgrid, Twitter, or Facebook to show us how you evaluated your limitations and made improvements. Now that we've made it to the end of our test, it's time for me to wrap up. Through today's workshop, we learned about the electrostatic forces of attraction and repulsion. We saw that opposite charges attract and the same charges repel. Using this knowledge, we tested the ability of different materials to build up a static charge. I hope you had fun experimenting, learned lots, and were able to create some sparks. I'm Adam from the Discovery Center, reminding you to stay curious and stay positive.